A recognizer can loop. A decider cannot loop. Loop just means go on forever. It just doesn't stop. Just keeps calculating. All right. Okay. Now it is talking about the distinction between deciders and recognizers. It's possible to convert, and where in the case of M1, the algorithm, the Turing machine, that recognizes the language of one variable polynomials that have integral roots, integral root. You can convert that into a decider. It can be done. In other words, for any string that comes in, the decider will either accept it or reject it. Right? By definition, that's what a decider Turing machine does. It either accepts or it rejects for all strings. Okay. How to do that? How to convert? Well, if you have a look at the particular polynomial we're talking about, single variable x, it was, you can't see it, but I can. It was 4x cubed minus 2x squared plus x minus 7. That was the polynomial. And if you think about it, if you're trying larger and larger and larger, you're trying all the integers for x. Okay. Now after a while, well, fairly soon, your 4x cubed term is going to absolutely dominate the others. Okay. So intuitively, you'd think there ought to be some kind of test. You put limits or bounds on the value of x, so that if you go over these bounds, outside these limits, outside these bounds, same thing, you know that it's just going to go on forever. Right? You know that the 4x squared term is going to dominate, and it can, and so that the polynomial can never be equal to 0. You will not be able to have the other terms, the other three terms, negate to 0. You cancel out, if you like, by subtraction. Cancel out the dominating, the influence of the first term of your 4x cubed. So intuitively, you feel there should be, if you can use bounds, and then you can test if the polynomial does not equate to 0 for all candidate roots, for all possible values of x inside those bounds. So if all those candidate roots, if they all equate to non-zero inside those bounds, well then you know that there is no root. Okay, and then you can reject. So by using bounds, you can convert the M1 machine from a decider into a more powerful, it has a greater, I have to be careful about power. You can convert it from a recognizer into a decider. Right? So all strings go in, and this modified M1 that uses bounds now in its algorithm, in its Turing machine, it can now make a decision on every string, whether it accepts it or rejects it. So it's now a decider. It decides. It doesn't just recognize certain cases. Right. So in problem 321, in the problem solving section of the text, the end of chapter 3, you're asked to show that the roots of a polynomial, their values, they have to. I think this is for a single valued polynomial. You have to show that they lie between these limits. So these are the bounds. So plus and minus, the upper and lower limit of little k times c max divided by c1. So what do these terms mean? Well, K is the number of terms in your polynomial. Like the one we had how many terms? 4. 4x cubed minus 2x squared plus x minus 7. So we had 4 terms. So for that case, K would be 4. And what's C max? That's the coefficient with the largest absolute value. Well, that would be minus 7. Okay. Well, the largest absolute value is 7. So I guess that's so C max would be minus 7. And what's C1? C1 that's the coefficient of the highest order term. Well, that would be 4 in the polynomial we're using. So the highest order term, it's x cubed. The highest order is 3 in the cube. So and its coefficient is 4. So C1 would be 4. So our bounds, if you do the math, so K is the number of terms, so that's 4. C max is 7. Divided by C1, which is 4. So that's 4 by 7 divided by 4, so that's 7. So your Turing machine M1, the algorithm then would be test all values of x lying between plus or minus 7, and if the polynomial is not 0 for all of those cases, then reject. There's no root. Okay, and showing the limits, the bounds as they're called, of the form plus minus k times C max divided by C1. That's one of the problems. Theorem, not theorem, problem 3.21. So that was an example of how to convert a recognizer into a decider. Right? The decider is more restrictive. It only has 2 options in its behavior. It either accepts or rejects, and it does that for all strings. A recognizer has 3 options for its behavior. It's less decisive, right? It could loop, it could go on forever and not make a decision. It could hum and ha all day, right? Okay, so now a bit of a comment before we get on to another topic. This guy Mati Jazovic, his proof, he did something similar. I guess one of the reasons why we've talked about this idea of how to convert, in this case, a recognizer into a decider, because it's relevant. It's sort of a lead-in, if you like, to how Matijasevic gave an answer to Hilbert's 10th problem. He did something similar in the sense he too worked with bounds, and and what Matijasevic did in his famous theorem was that it's impossible to calculate such bounds for the multivariable polynomials.